So we've seen how gravity distorts space and causes the way that light travels out to be essentially distorted, that the light cones become bent, such that if you get enough stuff in a single place, that light literally cannot leave that vicinity. All paths lead to the center. And this leads to the idea of a singularity, a point where essentially mass is concentrated with a horizon or a sphere around it, which effectively is a no-go zone, a place where once you pass, there is no way out. It's not a signpost, it's not a fence or anything, but it is a place that once you go past, there's no coming back from.
Yep, so this is a theoretical idea. This is what would happen if you have enough matter and you shrink it small enough. But the real question is, do they actually exist in the real world? I mean, there are plenty of theoretical things that could exist, and they're consistent, but don't actually happen to really occur. So presumably to form a black hole, you need to get an awful lot of mass and squeeze it down to a small enough size that it's inside its own event horizon. I mean, how could you actually physically do that? Wouldn't degeneracy pressure stop you?
So clearly, it's not going to be an easy thing to happen, and that's just as well. We don't need a universe full of black holes. Probably wouldn't be very good for our lives. But in the supernovae that I study, really big ones, we think maybe there's an avenue to form one. So the idea is that normally when supernova forms, the core shrinks down and is stopped by neutron degeneracy pressure. So the neutrons push back, and it turns out that if you have about 1.5 solar masses worth of stuff, the neutrons keep essentially the material at a radius of about 7 or 8 kilometers. And that is about 3 times bigger than the radius of a black hole. But if you get bigger and bigger stars, instead of being limited by maybe 1.5 solar masses in the center, we think that the process of the supernova isn't able to keep that much material out. And you'll pile on, and you can grow that central object to maybe 10, 20, or 30 times the mass of the sun.
So this would be a star that maybe started at 100 times the mass of the sun or something, might produce a 20 solar mass neutron star in the middle.
Right, but a 20 solar mass neutron star we think is a bit of an oxymoron, because if you take that degeneracy pressure, it turns out that when you add material to a neutron star, like a white dwarf, it tends to want to get a little smaller.
Yeah, and so the more mass of the neutron star, the smaller it is, not the bigger, because the extra pressure squashes it down, as we talked about for white dwarfs.
And there seems to be a crossover point of giving our understanding of neutrons and how they push on each other, that when you reach more than about 2 times the mass of the sun, the radius of the neutron star ends up being less than that no-go radius of the Schwarzschild radius. And so at that point, we think these things must become black holes.
Yes, at that point, because of course neutron stars, even the ones we know about, are not much bigger than the event horizon, so if you shrink it down by another factor of 2 or 3, it'll be inside its event horizon. And then, of course, the cones are tipped over, so no pressure can conceivably stop it from collapsing all the way, if our understanding of relativity is correct.
That's right. And so once you pass that, you're essentially end up with all paths leading to that single point, and you end up with this event horizon of a few kilometers across, and presumably a singularity in the center, created by a very massive star. Now, these massive stars are very rare, but we do see them even in our own galaxy and nearby galaxies, so we seem to know they exist. And we seem to have indication, especially gamma ray bursts. The only way we know how to get enough energy to form a gamma ray burst is to not have a 1 or 1.5 times the solar mass neutron star, but more like something that's 10 or 20 solar masses in the center.
Okay, so that's one way we could conceivably form black holes, but presumably there are some others, like if you had 2 neutron stars in close orbit, and we know there's at least one neutron star binary out there, they will lose energy because of gravity waves and presumably spiral together. And if they collided together and gave you something, again, over this roughly 3 solar mass limit, would that collapse to form a black hole?
Probably. Again, those collisions can be very messy. We think they may well also produce another form of a gamma ray burst, and for the gold and uranium in the universe as well. But the interesting question is as they come together, we think the less massive of the 2 neutron stars gets disrupted and sort of shredded to bits. And presumably most of that stuff is spinning around very quickly. And we think most of it will eventually collapse on to the other neutron star and form a black hole. There is some small chance that it would be ejected by the process and not fall on and bring the thing up. But that's a very good way to make another black hole, probably not a 10 solar mass one, but maybe a 3 solar mass one.
Would it also be possible to do it more gradually? I mean, we've talked about these X-ray binaries where you get a secondary star like Cygnus X1 dumping matter on a neutron star. Presumably if you dump more and more matter on it, it will get more and more massive, and at some point, just like we talked about for the Type 1a supernovae, it might go over this limit and collapse to form a black hole. Could that happen?
I think in principle it's possible, but I think in practice it's very difficult. And the reason is it's just very hard on a neutron star to actually get the material to settle down and go and settle on the neutron star. It produces so much energy that you will accumulate a little bit, but in order to have enough material settle down, in practice it looks pretty difficult to do that. And so I wouldn't be willing to rule it out, but I don't think we have any evidence at this point that it does happen.
Okay, so we've got this theoretical concept of black hole, and we've got some at least halfway plausible mechanisms to produce it, but it all relies on general relativity working in this regime of intense gravity where it's never been tested. I mean, in the lab, we can only test general relativity to maybe 1 decimal place or 2 decimal places. We can get rather more accurate measurements of it from the case of binary pulsars and things like that, where we can see the gravity wave coming out. But still, none of these tests come anything close to the conditions in a black hole. It's always very dangerous to take a theory and extrapolate it far beyond where it's been tested. So could it be that, in fact, they don't exist and that there's some new law of gravity that comes in when the gravitational forces become so big and stops it all happening?
Well, in science, as you know, nothing is ever ruled out. You always want to test, and since we haven't yet observed a black hole directly, it is certainly worthwhile to go out and look around the universe and see if what general relativity predicts is true, and to look for increasingly extreme cases to the point where maybe we eventually are able to find a black hole.
Okay, so in the next part of this course, we will talk about the observational evidence for the existence of black holes.